Hello, my friend. If you have trouble falling asleep, you're in the right place. What you may not realize about our world is that everything you have ever imagined when you picture the cosmos, every star, every planet, every glowing galaxy, may be only a small fraction of what truly exists. That is what makes dark matter such a fascinating and fundamental idea. It suggests that the universe is not simply stranger than it looks, but vastly deeper, with an invisible form of matter shaping galaxies, guiding cosmic structure, and influencing the fate of the cosmos itself. Few topics in science are as exciting as the possibility that most of reality is still hidden from view. So settle in, relax, and let this quiet mystery carry you gently into sleep. Chapter 1. What dark matter is and why we think it exists. When people first hear the phrase dark matter, it can sound like the name of something dramatic, almost mythical, as though astronomy has discovered a hidden substance waiting in the shadows between the stars. In reality, the idea is more careful than that. Dark matter is the name scientists give to whatever is producing a large amount of gravity in the universe without shining, glowing, reflecting, or otherwise interacting with light in the ways ordinary matter does. It is not called dark because it is black in color. It is called dark because it appears invisible to telescopes that collect electromagnetic radiation. We do not see dark matter directly. Instead, we infer that something is there because its gravitational pull affects the motion of stars, galaxies, and even light itself. That is the essential starting point. Dark matter is not an artistic metaphor, but a scientific label for an unseen source of mass whose effects appear across the cosmos. To understand why this idea became necessary, it helps to begin with a simple principle. Gravity depends on mass. If you know how much matter is present in a system and how that matter is distributed, you can estimate how strongly gravity should act. Astronomers can look at stars, gas, and dust, and from their light estimate how much ordinary matter is present. They can then compare that visible mass with the actual motions taking place. Over time, those two pictures did not match. Galaxies and clusters of galaxies behaved as though they contained far more matter than telescopes could detect. The mismatch did not vanish when measurements improved. Scientists were pushed toward a difficult conclusion. Either gravity behaves in a very unexpected way on large scales, or there exists a great deal of matter that does not reveal itself through light. One of the earliest major clues appeared in the early 1930s, when astronomer Fritz Zwicky studied the Coma cluster, a large collection of galaxies bound together by gravity. By examining how quickly the galaxies were moving, he found that the cluster should not have remained intact if it contained only the mass that astronomers could see. The visible matter did not appear to provide enough gravitational glue to hold the system together. Zwicky proposed that there must be additional unseen mass present. For many years, that idea remained more suggestion than accepted foundation, but later observations made it harder to ignore. The story of dark matter did not begin as a fashionable theory. It began as an attempt to account honestly for motions that ordinary matter could not explain. The case became much stronger in the 1970s through the study of galaxy rotation. In a spiral galaxy, stars orbit around the galactic center. If most of the mass were concentrated in the bright central regions, then stars farther out should generally move more slowly. But that is not what astronomers found. In many galaxies, stars far from the center were moving much faster than expected, and instead of dropping off sharply, the rotation speed stayed comparatively high at large distances. This suggested that galaxies are embedded inside much larger halos of matter than the luminous stars and gas alone would imply. Vera Rubin's observations helped make this conclusion difficult to dismiss, because the pattern appeared again and again. Galaxies did not behave like collections of visible matter alone. They behaved as though surrounded by enormous invisible reservoirs of mass. At this point, it is important to be precise about what scientists do and do not mean. Dark matter is not simply ordinary matter hidden by darkness, like a cold cloud or a faint object that does not shine much. Ordinary matter is made of familiar particles such as protons, neutrons, and electrons, and even when it is dim, it still interacts with light in traceable ways. It can absorb radiation, emit heat, block background light, or leave other signatures. Dark matter, as the evidence currently suggests, does not behave that way. It appears not to interact with the electromagnetic force in the same manner as normal matter. That is why it cannot be mapped with ordinary images in the direct sense. Its presence is reconstructed from gravity. The mystery is not merely that something is hard to see. The mystery is that a very large part of the universe seems to have mass while remaining almost entirely silent to our usual methods of observation. Another major reason scientists take dark matter seriously comes from gravitational lensing. According to general relativity, mass curves space-time, and light follows those curves. This means a sufficiently massive object can bend and distort the light of more distant objects behind it. Astronomers observe this effect in galaxy clusters and other massive systems. By measuring how background galaxies are stretched or magnified, they can estimate how mass is distributed in the foreground. Again, the result often shows more mass than visible matter can account for. This is powerful because it offers a method separate from stellar motions. Rotation curves tell one story. Lensing tells another. Yet both indicate that the universe contains hidden mass. When different observational techniques point toward the same conclusion, confidence grows. A famous example often discussed in this context is the bullet cluster, a system created by the collision of two galaxy clusters. In such a collision, the hot gas made of ordinary matter can slam into other gas, slow down, and heat up. But the dominant mass inferred from gravitational lensing appears displaced from much of that hot gas. In other words, the matter seen in X-rays and the mass traced by gravity do not line up in a simple way. This has been widely treated as some of the strongest visual evidence that most of the mass is not the same thing as the ordinary gas. It does not by itself solve the dark matter mystery, but it makes the picture harder to explain using only familiar matter. The evidence also reaches back into the early universe. Ancient light, known as the cosmic microwave background, preserves a record of conditions in the young cosmos, long before stars and galaxies fully formed. Space missions studying this radiation have measured tiny fluctuations across the sky with extraordinary precision. Those patterns encode information about the universe's contents and evolution. When cosmologists analyze them, the best-fitting model includes a large dark matter component in addition to ordinary matter. That means dark matter is not merely a local patch for a few odd galaxies. It appears in the broader cosmic recipe itself. Independent measurements of the microwave background and the later growth of large-scale structure both support a universe in which ordinary matter is only a minority of the total matter present. So what exactly is dark matter made of? The honest answer is that no one knows yet. Scientists are confident about many of its inferred properties, but not about its identity. It must contribute gravity. It must be abundant on cosmic scales. It must not interact with light the way ordinary matter does, or at least not strongly enough for us to have detected that interaction. Beyond that, several possibilities have been explored, including new particles not included in the standard model of particle physics. Large underground detectors, space observations, and particle accelerator experiments have all been used to search for clues. So far, none has delivered a confirmed discovery that settles the question. This uncertainty is important to emphasize because dark matter is an established scientific problem supported by substantial evidence, but its underlying nature remains open. It is also important not to confuse dark matter with dark energy. The two names sound similar, but they refer to different cosmic problems. Dark matter acts gravitationally like additional mass and helps explain how galaxies and larger structures hold together and evolve. Dark energy, by contrast, is the name given to whatever is driving the accelerated expansion of the universe on the largest scales. One helps account for missing gravitational pull inside cosmic structures. The other relates to the overall expansion history of space. When astronomers speak of dark matter, they are not talking about a mysterious pressure causing cosmic acceleration. They are talking about unseen mass inferred from gravitational effects. There is still room for caution, and science remains healthiest when it allows doubt. Some researchers have explored whether gravity itself might need modification on large scales rather than requiring unseen matter. These ideas continue to be discussed seriously, but dark matter remains the leading framework because it can account for a wide range of evidence at once: galaxy motions, cluster dynamics, gravitational lensing, the bullet cluster, the cosmic microwave background, and the growth of large-scale structure. The strength of the dark matter picture lies not in one dramatic observation alone, but in the way many observations fit together. That does not mean the case is philosophically complete. It means the current balance of evidence has convinced most of the scientific community that some non-luminous matter component is real, even though its microscopic nature is still unknown. In that sense, dark matter represents one of the most fascinating forms of scientific knowledge. It is a careful response to repeated gravitational patterns that ordinary matter does not explain well enough. We do not yet know the particle, if it is a particle. We do not yet know whether the final answer will be a new substance, a deeper theory, or something stranger than our present categories. But we do know that when astronomers weigh the universe by its gravitational behavior, the visible part does not add up to the total. The stars, planets, dust, and glowing galaxies seem to be only the illuminated fraction of a much larger structure. And perhaps there is something calming in that idea. The night sky does not have to reveal everything at once in order to be real. Even after a long day, you can let that mystery remain where it is, vast and quiet, while your thoughts grow lighter and the universe continues its patient work in the dark. Chapter 2: The First Clues Hidden in the Motion of Galaxies. The path toward the idea of dark matter did not begin with anyone setting out to discover an invisible substance. It began with a simpler effort, trying to understand motion honestly. Astronomers had long assumed that if they could see where the stars and galaxies were, and if they could estimate how much ordinary matter those luminous objects contained, then the pull of gravity should follow accordingly. The universe would still be vast and complicated, but its large-scale motions would at least remain accountable to what could be seen. What slowly unsettled that confidence was the repeated discovery that visible matter did not seem to provide enough gravitational pull to explain how galaxies and galaxy clusters actually moved. The first clues were not hidden in strange flashes or exotic particles. They were hidden in speed, orbit, and persistence. One of the earliest major hints came from the study of galaxy clusters. A galaxy cluster is not a single galaxy, but a great gathering of many galaxies held together by gravity. If the galaxies inside such a cluster are moving around rapidly, then the cluster must contain enough mass to keep them from flying apart. In the early part of the 20th century, astronomer Fritz Zwicky examined the Coma cluster and tried to estimate how much mass it would need in order to remain gravitationally bound. He compared the apparent brightness of the cluster, which gave a rough sense of how much ordinary luminous matter was present, with the speeds at which its galaxies were moving. The result was unsettling. The galaxies seemed to be moving too quickly for the visible mass alone to hold the cluster together. If the cluster contained only the matter astronomers could see, then its members should have escaped long ago. Yet the cluster remained intact. Something was missing from the mass budget. This was an important moment, but not yet a decisive one. Astronomy at that time still contained substantial observational uncertainty. Measuring distances was difficult. Estimating masses from brightness involved assumptions about what kinds of stars were present. Even the exact structure of galaxies and clusters was less clearly known than it is today. So Zwicky's conclusion was provocative, but not universally embraced. It suggested that the universe might contain unseen matter, but it did not force the scientific community to accept that conclusion at once. In science, especially when the claim is large, one anomaly is rarely enough. The idea had appeared, but it still needed reinforcement from other directions. That reinforcement came gradually through the study of individual galaxies, especially spiral galaxies. These are systems in which stars and gas orbit around a central region, often with sweeping arms extending outward into space. If most of a galaxy's mass were concentrated where most of its light was concentrated, then the outer parts should orbit more slowly than the inner parts, at least beyond the bright central regions. This expectation follows naturally from gravitational reasoning. Near a concentrated mass, speeds can remain high. Farther away, where less mass is enclosed and gravity weakens, orbital speed should decline. In a very broad sense, the outskirts of galaxies should behave somewhat like the planets of the solar system, where the more distant planets move more slowly around the sun than the closer ones. But galaxies did not cooperate with that expectation. As astronomers improved their instruments and began measuring how stars and gas moved at different distances from galactic centers, they found that the outer regions were not slowing down in the predicted way. Instead, the orbital speeds often remained unexpectedly high, even far beyond the brightest visible concentrations of stars. Rather than dropping off sharply, the rotation curves of many spiral galaxies stayed relatively flat. This was a profound clue because it did not concern a single unusual galaxy. The same pattern emerged again and again. The visible galaxy appeared to sit inside a much larger gravitational structure than the eye could detect. A key figure in making this case persuasive was Vera Rubin, working with Kent Ford and others. Rubin's observational work on galaxy rotation helped transform an interesting anomaly into one of the central problems of modern cosmology. By carefully measuring how matter moved in galaxies such as Andromeda, and then extending those measurements across many other spiral systems, she showed that the mismatch between visible matter and observed motion was not a fragile result. It was systematic. Galaxies were rotating as if they contained vast amounts of additional mass beyond what was visible in stars and gas. Her work mattered not merely because it was influential, but because it was careful, repeated, and consistent across many systems. This is often how science advances in practice. A strange idea becomes credible when it ceases to depend on a single dramatic case and instead begins appearing wherever you look closely enough. To appreciate why this was so powerful, it helps to picture what a rotation curve represents. Astronomers can use the light from stars or gas clouds to determine how fast those objects are moving toward or away from us. This is done through the Doppler effect, in which motion shifts the wavelength of light. By observing different parts of a galaxy, astronomers can reconstruct how quickly material is orbiting the center at different radii. Once this is done, the galaxy becomes not just an image, but a dynamical system. It begins to reveal how mass is actually distributed. When the outer rotation stays high instead of falling away, the implication is that substantial mass must continue extending outward as well. In other words, the galaxy's gravity does not end where most of its starlight fades. The visible galaxy seems to be only the bright inner region of something much larger. This point changed the conversation. The problem was no longer simply that a few galaxy clusters seemed too energetic to stay bound. Now even ordinary spiral galaxies appeared to contain hidden mass. That made the issue harder to dismiss as a measurement error or a local peculiarity. It suggested that the discrepancy between light and gravity was woven into the structure of galaxies themselves. The first clues, then, were deeply kinematic. They came from motion read carefully, not from what galaxies looked like, but from how they behaved over time under the rule of gravity. The evidence also had a certain elegance because it relied on a basic scientific habit, comparing expectation with observation. Astronomers did not invent a mystery first and then go looking for support. They measured motion, applied known gravitational reasoning, and found that the visible matter fell short. In that sense, dark matter entered astronomy not as a leap into fantasy, but as a conservative response to repeated discrepancies. If the observed motions are real, and if gravity behaves in the standard way on these scales, then additional mass must be present. This is why the early history of dark matter is really a history of accounting. The universe seemed to weigh more than it's shown. As measurements improved, the picture became even harder to avoid. Radio observations of neutral hydrogen were especially useful because gas could often be traced farther out than starlight. That meant astronomers could follow galactic rotation well beyond the bright optical disk. The result again pointed in the same direction. The outer regions remained dynamically active, where the visible mass alone suggested they should have been calmer. The hidden component was not confined to galactic centers. It seemed extended, diffuse, and enormous. This is where the modern concept of a dark matter halo began to take shape. Not a compact, invisible object, but a broad distribution of unseen mass surrounding and permeating the galaxy. Importantly, these observations did not mean that everything in the galaxy was misunderstood. Ordinary matter still mattered tremendously. Stars, gas, dust, stellar remnants, and the complex physics of galactic formation remained real and measurable. But the motions implied that these familiar components were embedded in a larger gravitational environment. The visible parts of galaxies seemed almost like luminous islands inside a more massive invisible sea. Once that idea took hold, many other questions followed. How did such halos form? What were they made of? Did they help galaxies assemble in the early universe? But those larger questions came later. The first task was simply to recognize that the motions themselves were trying to say something. There were, of course, reasons to be cautious. Astronomers had to be sure that the discrepancy was not being produced by bad distance estimates, misread brightness profiles, or incomplete understanding of stellar populations. They had to compare many galaxies, not just one. They had to measure with better instruments and more careful corrections. That caution strengthened the case rather than weakening it. The more the observations were refined, the more stable the central result became. The hidden mass problem survived scrutiny. It was not washed away by better data. It sharpened under it. By the time this pattern had been seen across clusters and galaxies alike, astronomy had reached an uncomfortable but fertile point. The visible universe no longer seemed to be the whole gravitational universe. Light had ceased to be a complete guide to mass. This was a profound shift because astronomy had always depended so deeply on electromagnetic observation. Telescopes gather light, and from light we infer temperature, composition, distance, and motion. But now the motions were insisting that some major part of reality was not announcing itself through light at all. The first clues hidden in the motion of galaxies therefore carried a philosophical weight as well as a scientific one. They suggested that the universe could be measured accurately and still remain largely unseen. That is one reason the history of dark matter remains so compelling. It reminds us that reality is not obligated to match our first intuitions. A galaxy may appear to be a shining spiral of stars suspended against darkness, and yet its visible form may be only the trace of a much larger, invisible structure. We learned this not because the universe explained itself clearly, but because motion betrayed what appearance concealed. The galaxies were moving too quickly, holding together too well, rotating too steadily. The evidence came not as a declaration, but as a pattern of quiet insistence, and perhaps that carries a gentle reflection with it. Much of existence may be shaped by things we do not directly see, yet their presence can still be known by the paths they guide and the structures they hold together. In that sense, the universe can feel mysterious without becoming hostile, vast without becoming empty, and as the day recedes, there is something strangely comforting in the thought that even the hidden parts of reality still leave their trace in motion. Chapter 3. Why gravity seems stronger than visible matter allows. To say that gravity seems stronger than visible matter allows is really to say that the universe does not appear to weigh only what it shines. Astronomers estimate how much matter seems to be present from the light it gives off, and then compare that estimate with how strongly gravity appears to act. If those two measurements agree, then visible matter is enough. If they do not agree, then something in the picture is missing. Over time, astronomers found that in many cosmic systems, the gravitational pull seemed too large for the observed stars, gas, and dust to account for. The mismatch appeared not as a vague feeling, but as a repeated physical problem. Motions were too fast, structures were too stable, and light from background objects was bent too strongly. The logic behind this is simple. Gravity shapes the motion of astronomical systems on large scales. A star orbiting within a galaxy, or a galaxy moving within a cluster, responds to the total mass around it. If astronomers can estimate that mass from luminous matter alone, then they can form an expectation for how fast those objects should move. Light tells them where stars are, how much gas is present, and roughly how much ordinary matter those components contain. But gravity does not care whether matter is bright or easy to photograph. It responds only to mass and energy. So when the observed motion does not match the mass inferred from visible material, astronomers are forced to ask whether something invisible is contributing additional gravitational pull. This is where the distinction between seeing matter and weighing matter becomes crucial. Telescopes are excellent at collecting light, but light is not the same thing as mass. A bright region can contain relatively little matter if it is filled with hot luminous stars. A dim region can contain much more matter if it is made of faint stars, cold gas, or something else entirely. Astronomers therefore estimate mass from brightness using the known behavior of stellar populations, gas clouds, and other ordinary components. These methods are grounded in spectroscopy, stellar evolution, and observations across many wavelengths. Yet even after accounting for visible stars, dust, and gas, the gravitational pull in many systems still comes out too large. That is why the dark matter problem is not just a problem of poor visibility. It is a problem of gravitational bookkeeping. In galaxies, this tension shows up most clearly in orbital motion. Material farther from the center responds to the mass enclosed within its orbit. If most of the matter were concentrated, where most of the starlight is concentrated, then the outer regions should generally rotate more slowly once they extend beyond the brightest parts of the disk. But the measured speeds often remain unexpectedly high far from the center. That means the pull of gravity continues to be strong in places where the visible matter has already thinned out. In effect, the galaxy behaves as though a large amount of mass keeps extending outward, even after the luminous structure begins to fade. The visible galaxy does not appear to mark the true edge of its gravitational influence. This can be understood in an intuitive way. In a galaxy, the stars provide the visible pattern, but the motion of those stars reveals the deeper structure. Astronomers are not merely admiring the shape of a galaxy. They are reading how fast matter moves through the galaxy's gravitational field. The motion becomes a hidden map. And in system after system, that map says that the mass extends well beyond the bright stellar disk. The galaxy's light fades, but its gravity does not fade as quickly. Galaxy clusters make the same lesson even harder to ignore. These are vast systems containing many galaxies, along with enormous clouds of hot gas that fill the space between them. That hot gas is important because one might hope that the missing gravity was simply hiding in ordinary matter that was difficult to see. In clusters, astronomers can actually detect a great deal of this ordinary matter through X-rays emitted by the hot intracluster gas. In many clusters, that gas contains more ordinary mass than the galaxies themselves. And still, it is not enough. When the motions of galaxies in clusters are measured, and when the total mass is inferred from the cluster's gravitational behavior, the ordinary matter still falls short by a large margin. This means the discrepancy survives even after astronomers include not just stars, but also massive reservoirs of visible baryonic gas. Another way to say this is that the problem became stronger as astronomy improved. Better telescopes did not cause the discrepancy to disappear. They allowed astronomers to find more normal matter than before, especially hot gas in clusters and diffuse gas in and around galaxies. But even after those additions, gravity still seemed too strong. The universe was not merely dimmer than expected. It appeared more massive than expected. Gravitational lensing adds another layer to the argument because it provides a way to weigh matter without relying on the internal motion of stars or galaxies alone. According to general relativity, mass curves space-time, and light follows those curves. If a massive object lies between us and a more distant source, it can distort and magnify the background light. Astronomers can measure these distortions and reconstruct how much mass must be present in the foreground object. When they do this for galaxy clusters and other large structures, they often find more mass than ordinary luminous matter can supply. This matters because it is an independent method. The same conclusion emerges from a different kind of evidence. Gravity appears stronger than visible matter allows not only because objects move too quickly, but also because light bends as though more mass is present than telescopes can directly account for. This is part of what gives the dark matter framework its strength. It is supported by several different ways of inferring mass. Orbital motion points in one direction. Cluster dynamics point in the same direction. Gravitational lensing points there as well. On still larger scales, the growth of cosmic structure and the patterns preserved in the cosmic microwave background also fit a universe in which ordinary matter alone is not enough to produce the gravitational scaffolding we observe. The mismatch is not isolated to one corner of astronomy. It shows up across the history and architecture of the universe. There is also an important physical reason why ordinary matter alone struggles to explain the observed structure of the cosmos. Ordinary matter interacts with light. In the early universe, before atoms formed in a stable way, ordinary matter was tightly coupled to radiation. That coupling resisted the growth of dense clumps, a non-luminous matter component that did not interact strongly with light could begin helping structure form earlier and more efficiently. In modern cosmology, dark matter plays that role. It provides gravitational wells into which ordinary matter later falls. This helps explain why galaxies and clusters formed in the patterns we observe today. Still, the phrase "stronger than visible matter" allows must be handled carefully. Gravity itself is not being shown to become magically stronger in some places. Rather, when scientists calculate how much gravity should arise from the ordinary matter they can detect, the answer comes out too small. Something is missing from the inventory. The leading interpretation is additional matter that does not emit or absorb light in the familiar way. Some alternative ideas propose that gravity changes behavior on large scales instead. These proposals have scientific interest, but dark matter remains the dominant explanation because it accommodates many different kinds of evidence at once, especially when clusters, lensing, and cosmological structure are considered together. It is worth lingering on the humility built into this problem. Astronomy began as the science of visible things. The sky offered stars, planets, nebulae, and galaxies, all accessible through light. Yet the dark matter question reveals a limit hidden within that success. Light can reveal an enormous amount, but not everything that matters gravitationally. The universe can be measured with great precision and still remain partly concealed. That is not a failure of science. It is one of science's deepest successes. The method was strong enough to discover that the visible account was incomplete. That incompleteness has changed how astronomers think about almost every large cosmic system. A galaxy is no longer understood as merely the stars it contains. A cluster is no longer just a gathering of galaxies with hot gas between them. These visible components are now interpreted within broader halos and structures whose dominant mass is unseen. The luminous parts are still real and essential, but they are not the whole gravitational story. A galaxy can look light and still be heavy. A cluster can seem sparse and still hold vast mass. And yet, for all its importance, dark matter remains unnamed in the deepest sense. We know what role it seems to play, but not what it is. We know the gravity it contributes, but not the particle or principle behind it. That mixture of confidence and ignorance is one of the most honest states in science. It allows knowledge to grow without pretending to be complete. Gravity seems stronger than visible matter allows, because the universe is telling us that visibility was never the same thing as total reality. There is something quietly existential in that. The cosmos may be held together in part by what never shines, and the structures we admire may rest on foundations we do not directly see. Perhaps that is not only a scientific lesson, but a gentler one as well. Reality is often deeper than appearance, and even in darkness, something may still be there, shaping the whole. Chapter 4: Dark Matter and the Hidden Structure of Galaxies. A galaxy can look complete when seen through a telescope. There is the bright central region, the extended disk, the spiral arms in some systems, the older stars in the bulge, the scattered clusters, the dust lanes, and the faint outer glow that softens into intergalactic darkness. But modern astronomy suggests that this visible form is not the full structure of a galaxy. What we see in starlight appears to be only the luminous portion of a much larger system, one embedded within a vast halo of unseen matter. In that sense, a galaxy is not just a collection of stars. It is a visible pattern suspended inside a deeper gravitational framework. That hidden framework is one of the main reasons galaxies have the shapes, motions, and histories they do. The idea of a dark matter halo is central here. Astronomers use that term to describe the broad, roughly spherical distribution of invisible mass that appears to surround a galaxy and extend far beyond its bright stellar disk. In spiral galaxies, the visible stars trace out a flattened rotating structure, while the inferred dark matter component seems much more extended and less concentrated into the thin disk itself. The halo is not thought of as a sharp shell with a clean outer edge. It is better imagined as a diffuse gravitational envelope, permeating the region around the galaxy and contributing most of the galaxy's mass. The luminous part is therefore only the inner, shining inhabitant of a much larger and mostly unseen system. This changes the way astronomers interpret galactic structure. A spiral galaxy does not simply rotate in isolation because of the stars and gas visible in its disk. It rotates within the gravitational potential of the surrounding halo. The spiral arms, the long-term survival of the disk, the motions of stars in the outskirts, and the behavior of gas at large radii are all influenced by that deeper mass distribution. The visible galaxy is therefore not the whole machine. It is the most illuminated component of a larger gravitational architecture. If the halo were absent, the galaxy would not merely look lighter. Its overall structure and dynamical behavior would be significantly different. The Milky Way is a useful example because it lets astronomers study galactic structure from within. Our galaxy has a thin disk of stars and gas, a thicker stellar component extending above and below the plane, a central bulge, globular clusters orbiting farther out, and a faint stellar halo made of older stars. Yet astronomers believe the Milky Way, like most galaxies, is embedded in a much larger halo of dark matter. This unseen component helps explain the motions of stars and satellite galaxies around the Milky Way and the way the galaxy fits into the broader cosmological picture of galaxy formation. The stars we see overhead on a clear night belong to a visible structure that is only part of the galaxy's full mass. Dark matter also helps explain why galaxies were able to form in the first place. In the standard cosmological picture, dark matter provided the first strong gravitational scaffolding on large scales. Ordinary matter, because it interacts with radiation and can cool, later fell into those dark matter potential wells and began forming the dense luminous structures that eventually became galaxies. In this view, the halo is not an afterthought surrounding the finished galaxy. It is one of the conditions that made the galaxy possible. Stars form inside gas clouds, but the overall galactic environment in which that gas collects and remains bound is shaped by the halo. The hidden structure comes first in a gravitational sense, and the visible structure grows within it. This relationship between visible matter and hidden matter is especially important when comparing different kinds of galaxies. Large spiral galaxies, elliptical galaxies, dwarf galaxies, and ultra-diffuse systems do not all contain the same proportion of stars relative to total mass. Some galaxies seem especially efficient at turning gas into stars. Others do not. Dark matter halos help provide a unifying framework for understanding that diversity. A halo's mass, concentration, merger history, and environment can all influence how gas cools, whether star formation proceeds steadily or violently, and how much of the baryonic matter ends up in luminous form. Two galaxies may shine very differently while still inhabiting halos that reveal deeper structural similarities. Dwarf galaxies are particularly revealing in this respect. These small galaxies often contain relatively few stars compared with larger systems, yet the motions of those stars can imply substantial dark matter content. Rubin Observatory educational material notes that dwarf galaxies have their own dark matter halos, unlike star clusters, whose stars move under the gravity of their visible mass alone. This distinction matters because dwarf galaxies and star clusters can sometimes look superficially similar at first glance. Both may be faint, compact, and made of old stars. But dynamically, they are not the same. The presence of a dark matter halo gives a dwarf galaxy a deeper structural identity. It is not just a loose collection of stars. It is a small galaxy because it sits within a genuine halo. That difference also helps astronomers classify faint objects in the outskirts of larger galaxies. When a small stellar system is discovered orbiting the Milky Way or another large galaxy, one of the key questions is whether it is a star cluster or a dwarf galaxy. The answer is not based on appearance alone. It depends on how the stars move and whether their motion suggests the presence of dark matter. This means the hidden structure is often more fundamental than the visible one. A system becomes recognizable as a galaxy not simply because of how it looks in an image, but because of the deeper gravitational environment it inhabits. Dark matter halos are also thought to contain substructure. Simulations of galaxy formation in the cold dark matter framework show that a large halo like the Milky Way's should not be perfectly smooth. Instead, it should contain many smaller clumps and subhalos, some of which may host dwarf galaxies, while others remain almost completely dark. NASA material describing simulations of the Milky Way halo shows a swarm of such dark matter concentrations around our galaxy. This substructure matters because it may shape the distribution of satellite galaxies, influence tidal streams of stars torn from smaller systems, and preserve part of the galaxy's merger history in invisible form. Galaxies are not static objects, and dark matter halos are deeply involved in their growth through mergers and accretion. Over cosmic time, smaller halos fall together to form larger ones, and the galaxies inside them can merge as well. The visible signs of these events may include distorted disks, tidal tails, shells, stellar streams, and bursts of star formation. But behind those luminous signatures lies the larger process of halo assembly. A galaxy's present structure therefore reflects not only the stars it has formed, but also the long accumulation of dark matter and the collisions of halos through cosmic time. In this sense, the hidden structure is also a historical record. It stores the memory of how a galaxy became what it is. Even the outermost parts of galaxies, where starlight becomes extremely faint, can reveal something about this hidden architecture. Streams of stars pulled from disrupted dwarf galaxies curve through the halos of large galaxies like delicate ruins. These streams trace the gravitational field through which they move, and astronomers use them to probe the mass distribution of the surrounding halo. The stars are visible, but what gives those streams their shape over time is the larger invisible structure through which they travel. A galaxy therefore extends beyond its obvious body. Its true reach includes faint stellar debris, hot gaseous halos, orbiting satellites, and the still larger dark matter halo that gives the entire system coherence. There are also puzzles within this picture, and those puzzles are part of what makes the science alive rather than settled in every detail. Not every galaxy behaves in exactly the way simple dark matter models once suggested. NASA has reported on unusual cases, such as galaxies that appear to contain much less dark matter than expected. Such objects do not erase the broader evidence for dark matter halos, but they do remind astronomers that galaxy formation is complicated. The interplay between dark matter, gas dynamics, feedback from stars, and environmental effects can produce systems that do not fit the easiest version of the story. The hidden structure is real, but the visible outcomes are diverse and sometimes surprising. That complexity is actually part of the strength of the modern view. Dark matter is not treated as a magical answer to every galactic question. Rather, it provides the large-scale gravitational framework inside which many additional processes unfold. Gas cools or fails to cool. Stars form quickly or slowly. Supernovae stir and expel material. Black holes may regulate central regions. Tidal interactions reshape disks. And through it all, the halo remains the broad invisible stage on which those visible events occur. The galaxy's luminous anatomy makes sense most fully when placed inside that larger context. So when astronomers speak of the hidden structure of galaxies, they do not mean a poetic secret tucked behind the stars. They mean something physically consequential, that galaxies are organized by a mass distribution we cannot image directly in ordinary light, yet can infer through motion, lensing, and cosmological modeling. The disk, bulge, stellar halo, and satellite system are all nested within this deeper framework. What appears graceful and luminous from afar is sustained by something more extended, more massive, and mostly invisible. The galaxy we see is real, but it is incomplete when taken alone. Perhaps that is one of the quietest lessons dark matter offers. A galaxy can be beautiful in what it reveals, and still owe much of its form to what remains unseen. The visible universe may be only the bright surface of a deeper order, and there is something strangely calming in that thought, that even hidden structure can hold things together, shaping light from within the dark. Chapter 5. The Cosmic Web: How Dark Matter Shapes the Universe. When astronomers look far beyond individual galaxies, they do not find a universe in which matter is scattered evenly in all directions. On the largest scales, galaxies gather into groups, clusters, superclusters, long filaments, broad sheets, and immense empty regions called voids. This vast arrangement is often described as the cosmic web. It is not merely a poetic image. It is the large-scale structure of the universe itself, a pattern in which dense regions are connected by thinner bridges of matter, while enormous underdense spaces open between them. Modern cosmology holds that dark matter plays a central role in building this web, providing much of the gravitational framework along which ordinary matter later collects. The importance of dark matter at this scale comes from how structure grows. The early universe was remarkably smooth, but not perfectly smooth. Tiny variations in density were present in the distribution of matter and energy. Regions that were slightly denser than average possessed slightly stronger gravity, and that stronger gravity allowed them to attract still more matter. Over time, these small imbalances grew. According to NASA's overview of the cosmic web, the early distribution of matter was close to uniform, with slight density variations that later developed into a web-like pattern of filaments and sheets. In this picture, dark matter is not a minor detail added later. It is a major part of the reason the universe developed a large-scale architecture at all. This idea changes the meaning of what a galaxy is. A galaxy is not just an isolated island of stars floating independently in darkness. It is part of a much larger environment shaped by the surrounding distribution of matter. Galaxies tend to sit where the web is denser, often along filaments or at the intersections where filaments meet. Those intersections are especially important because they are places where matter accumulates most strongly, giving rise to galaxy groups and clusters. NASA describes the web as a sort of scaffolding that cradles everything that exists within the universe. In other words, galaxies are not arranged at random. Their positions reflect the deeper geography of matter on cosmic scales, much of it dark. One of the reasons dark matter is so effective in this role is that it does not interact with light in the same way ordinary matter does. Ordinary matter in the early universe was strongly coupled to radiation for a significant period, and that interaction resisted the rapid growth of dense, small structures. Dark matter, by contrast, did not remain tied to light in the same way. so it could begin clumping under gravity earlier and more freely. As those dark matter clumps grew, they created gravitational wells into which ordinary matter later fell. That process helped guide where gas accumulated, where stars eventually formed, and where galaxies emerged. The visible universe, in this framework, grew inside an invisible skeleton that had already begun to take shape. This is why the cosmic web is often described first in terms of dark matter rather than starlight. To human eyes or ordinary optical telescopes, the filaments themselves are not always obvious. What stands out most clearly are galaxies, especially where they cluster in large numbers. But the galaxies are only the brightest markers of a deeper matter distribution. NASA's recent web-based mapping work describes dense regions of dark matter connected by lower density filaments, with ordinary matter tending to trace that same underlying structure. That does not mean the visible matter and dark matter are identical. It means the visible matter appears to have followed the gravitational paths laid down by the dark component over cosmic history. The web is not static. It evolves across cosmic time. Regions of slightly enhanced density continue drawing matter inward, making filaments more pronounced and clusters more massive. NASA's Hubble mapping work showed that dark matter clumping becomes more pronounced from the earlier universe to the more recent universe, confirming the broad expectation that structure grows over time. This matters because the cosmic web is not just a snapshot of where matter happens to be now. It is the result of a long history of growth, collapse, inflow, and accumulation. The universe did not begin with ready-made walls and filaments. It developed them gradually under gravity. At the intersections of the web, the density of matter becomes especially high. These regions give rise to galaxy clusters, some of the largest gravitationally bound systems in the universe. NASA's discussion of the giant filament associated with the cluster MAX J0717 describes matter streaming along the filament into an already crowded region. This is a powerful image of how the web behaves. Filaments are not decorative strands. They are channels through which matter moves and accumulates. Over immense spans of time, they help feed clusters, shape the growth of large structures, and connect one dense region of the universe to another. The web is therefore not only spatial structure, but dynamical structure as well. It guides flow. The existence of vast voids between filaments is just as important as the filaments themselves. The large-scale universe contains enormous underdense regions where relatively few galaxies are found. NASA describes the cosmic web as a pattern of concentrations of galaxies with voids of space in between, almost as though the galaxies rest on the surfaces of enormous empty bubbles. This contrast between crowded nodes and quiet voids is one of the most striking signatures of large-scale structure. Gravity tends to amplify differences. Places that begin slightly denser grow richer in matter, while places that begin slightly emptier tend to lose relative importance as matter flows elsewhere. The web and the voids are complementary outcomes of the same process. Modern observations have gone beyond inferring this structure indirectly. Space missions and lensing surveys now allow astronomers to map the large-scale distribution of unseen matter more directly through its gravitational effects. Hubble created one of the first three-dimensional maps of the web-like distribution of dark matter by combining many overlapping images and using gravitational lensing. Planck produced an all-sky view of the projected dark matter distribution by measuring the tiny distortions imprinted on the cosmic microwave background as that ancient light passed through cosmic structures. More recently, Webb has produced one of the sharpest dark matter maps yet, revealing the same web-like pattern with improved detail. Roman is expected to map the large-scale distribution of both seen and unseen matter across a far larger area of sky. Together, these efforts have strengthened the picture of a universe whose largest structures are governed by an invisible mass component. The cosmic web also helps explain why galaxies appear where they do and why their environments matter so much. A galaxy born along a thick filament and near a cluster can live a very different life from one in a more isolated region. Dense environments encourage interactions, mergers, stripping of gas, and the growth of large systems. More isolated environments can preserve quieter evolutionary histories. The web, therefore, acts not only as a large-scale pattern, but as a context for galaxy evolution. To know a galaxy fully, one must know something about its place in the web. It is shaped not only by its own stars and gas, but by the larger matter currents around it. This makes the universe feel less like a collection of separate objects and more like a connected structure. There is also a subtle theoretical lesson in how the web forms. Not every kind of dark matter would produce the same structure. ESA's discussion of cosmic structure formation notes that hot dark matter and cold dark matter lead to very different growth patterns. In hot dark matter models, fast-moving particles smooth out small-scale structure, while observations of the early universe instead show that smaller objects emerge first and later build into larger systems. This has been one of the reasons cosmologists concluded that most dark matter must be cold, meaning slow enough to allow smaller structures to survive and grow. So the shape of the web does not merely indicate that unseen matter exists. It also carries clues about what that matter must be like. All of this gives dark matter a role that is broader than simply adding extra mass to galaxies. On the scale of the cosmic web, dark matter appears as an organizing principle. NASA describes it as shaping the cosmos and organizing galaxies and cosmic objects on a large scale. Without that organizing influence, the visible universe would likely have developed very differently. Webb researchers even note that by helping matter gather earlier, dark matter may have given the universe more time to form stars, forge heavier elements, and eventually allow planets like Earth to exist. That does not make dark matter mysterious in a mystical sense. It makes it foundational in a physical one. The large structures of the universe, and perhaps some of the conditions that made life possible, seem to be tied to a substance we still cannot identify directly. So the cosmic web is not only a map of where galaxies ended up, it is the visible imprint of a deeper gravitational history. It tells us that the universe grew from slight irregularities into an immense connected network, and that dark matter was central to that growth. Filaments, clusters, and voids are not separate curiosities. They are the mature expression of gravity working over time through a cosmos in which much of the matter is unseen. The web is the large-scale memory of that process, stretched across the observable universe. And there is something quietly humbling in that image. The galaxies we notice most easily may be only the bright knots on a much larger unseen framework, connected across distances too vast to feel in ordinary life. Perhaps that is one of the gentler truths of cosmology, that even in a universe filled with darkness, structure can still emerge, and what seems scattered at first can belong to a deeper hidden order. Chapter 6. What dark matter is not. By the time astronomers began taking dark matter seriously, one of the first scientific tasks was not only to ask what it might be, but also to ask what it could not be. That question matters because many things in the universe are dark in the everyday sense. Some objects shine only faintly. Some are hidden behind dust. Some emit light mostly outside the visible range. Some are compact, cold, distant, or difficult to detect. So if a large amount of mass seems to be missing, the first reasonable thought is not necessarily that the universe contains a new kind of matter. The first thought is often simpler. Perhaps the missing mass is just ordinary matter in forms that are hard to see. The history of dark matter includes a long process of testing that possibility and finding, again and again, that it is not enough. The most basic clarification is that dark matter is not just ordinary matter sitting in darkness. Ordinary matter, in the language of physics, means baryonic matter, the familiar matter made of protons and neutrons, along with electrons. Stars, planets, gas clouds, dust grains, people, oceans, rocks, and the atmospheres of worlds are all forms of ordinary matter. This kind of matter interacts with light and with the rest of the electromagnetic spectrum. It may glow brightly like a star or only weakly like a cold cloud, but it still leaves electromagnetic signatures that astronomy can search for. A truly invisible ordinary object is difficult to maintain across many lines of evidence because ordinary matter tends to absorb, emit, scatter, or otherwise affect radiation in detectable ways. Dark matter is different precisely because the evidence suggests that it does not interact with electromagnetic radiation in the usual manner. It is inferred primarily through gravity, not through emitted light or absorbed starlight. This is one reason why dark matter is not the same thing as cosmic dust. Dust can certainly hide objects, redden starlight, and make some regions of space opaque in visible wavelengths. But dust is made of ordinary atoms. It absorbs and re-radiates energy, especially in infrared wavelengths. Astronomers have many ways of detecting it. Entire branches of astronomy are built around mapping dust, gas, and other faint baryonic components. So while dust can complicate observations, it cannot explain the full dark matter problem. The missing gravitational mass implied by galaxies, clusters, gravitational lensing, and cosmological measurements is far too large and too broadly distributed to be explained by ordinary dust clouds that simply escape notice. For many years, astronomers considered whether dark matter might instead consist of compact ordinary objects that are dim or nearly invisible. These were often grouped under the name MACOs, meaning massive compact halo objects. The category included things like brown dwarfs, faint white dwarfs, neutron stars, rogue planets, and certain kinds of black holes. These objects are dark or nearly dark in ordinary images, and because they are made from conventional matter, they seemed at first like a conservative solution. Perhaps galaxies were simply surrounded by huge populations of dim bodies that added mass without much light. This was an attractive idea because it did not require new physics. It only required that much of the universe's matter had ended up in hard-to-see objects. But that idea faced severe observational limits. If large numbers of compact objects filled galactic halos, their gravity should occasionally reveal them through microlensing, a process in which a compact mass briefly magnifies the light of a background star as it passes in front. Astronomers carried out extensive microlensing surveys, especially toward the Magellanic Clouds in the galactic bulge, to look for this effect. These searches did find some compact objects, which is no surprise because the universe does contain brown dwarfs, stellar remnants, and other dim bodies. Yet the results did not support the idea that most dark matter is made of MACOs. NASA's recent summary of Hubble work states that observations have ruled out a leading explanation in which dark matter is mainly composed of small black holes and other compact baryonic objects across a very wide mass range. The conclusion was not that such bodies do not exist, but that they cannot account for most of the missing mass. This leads naturally to another common misconception. Dark matter is not simply black holes in general. Black holes are real, important, and fascinating, but they are not the broad solution to the dark matter problem. Ordinary stellar black holes form from the deaths of massive stars, and their abundance is constrained by the number of such stars that could have existed. Supermassive black holes sit in galactic centers, but they are concentrated in very small regions and do not supply the extended halo-like distribution required to explain galaxy dynamics. Primordial black holes, hypothetical black holes formed in the early universe, remain scientifically interesting in some limited mass windows. But the idea that all or most dark matter is made of black holes has been strongly constrained by lensing and other evidence. So while black holes can contribute some mass in specific places, dark matter is not simply another name for the known black holes already present in the cosmos. Dark matter is also not antimatter. This confusion is understandable because both words can sound dramatic and exotic, and both belong to modern physics. But antimatter is not invisible in the same way dark matter is thought to be. Antimatter particles have the same mass as their matter counterparts, an opposite electric charge. Positrons, for example, are the antimatter partners of electrons. Antimatter interacts electromagnetically, which means it can emit, absorb, and respond to light and fields. More importantly, when matter and antimatter meet, they annihilate and produce other particles and radiation. If the universe's dark matter were mostly ordinary antimatter, it would leave very strong observational signatures at the boundaries where it encountered normal matter. Those signatures are not seen at the level required. Dark matter and antimatter belong to different scientific questions. One concerns the hidden mass of the universe. The other concerns symmetry between particles and antiparticles. Nor is dark matter the same thing as dark energy. The names are similar because both refer to components of the universe that are not directly visible in ordinary light, but they solve different problems. Dark matter behaves as an additional gravitating component that helps explain how structures form and how galaxies and clusters behave. Dark energy, by contrast, is the name given to whatever is driving the accelerated expansion of the universe on the largest scales. One acts like unseen mass pulling through gravity. The other is invoked to explain a large-scale cosmic acceleration. These are separate concepts supported by different lines of evidence, and they should not be blended together. Calling dark matter dark does not place it in the same category as dark energy any more than a similar adjective makes two physical phenomena identical. Another important point is that dark matter is not just ordinary hot gas that astronomers failed to count. Hot gas does exist in large amounts, especially in galaxy clusters, and modern X-ray astronomy has revealed enormous baryonic reservoirs that earlier generations could not easily measure. But even after these baryonic components are included, the gravitational discrepancy remains. The improvement of astronomy actually strengthened the problem. Better instruments found more normal matter, yet still not enough. This is one reason the dark matter hypothesis became more compelling over time, rather than fading away. The missing mass was not simply a bookkeeping failure caused by ignoring diffuse gas. The gap shrank in some places as observations improved, but it did not disappear. There is an even deeper reason why dark matter cannot be mostly ordinary baryonic matter. Measurements of the early universe, especially from the cosmic microwave background and from primordial nucleosynthesis, constrain how much ordinary matter exists overall. Those measurements agree that baryons make up only a limited fraction of the total cosmic content. NASA's WMAP overview summarizes this clearly by noting that dark matter is matter not made of atoms. In other words, the universe simply does not contain enough atom-based matter to explain the dark matter phenomenon, even before one asks how bright or dim that matter might be. This is a crucial result because it moves the discussion beyond astronomy alone and into cosmology. The universe was measured in its early state, and that early measurement already says that most matter is not ordinary atomic matter. It is also worth saying that dark matter is not a placeholder for ignorance in a lazy sense. Scientists are not using the term dark matter to avoid explanation. The phrase does mark an unknown, but a constrained unknown. It refers to something that must have mass, must shape gravitational structure, must be largely non-luminous, and must fit a body of cosmological evidence that ordinary baryonic matter, dust, black holes, and antimatter do not adequately satisfy. That is why modern candidates for dark matter usually involve new non-baryonic particles rather than merely rearrangements of familiar stuff. The field remains open because the final identity is still unknown, not because there are no boundaries around the problem. So Chapter 6 is really a chapter about scientific elimination. Before knowing what dark matter is, astronomy had to learn what it is not. It is not hidden dust, not dim ordinary stars, not a vast population of brown dwarfs, not the known black holes distributed through space, not antimatter, not dark energy, and not simply overlooked gas. Each of those possibilities was worth considering, and each helped sharpen the question. Science often moves this way. It narrows the field patiently. It removes the familiar explanations one by one until what remains, however strange, begins to look necessary. And there is something quietly reflective in that process. The universe sometimes teaches not by revealing itself immediately, but by refusing every easier answer first. What remains after those refusals may still be hidden, but it is no longer shapeless darkness. It is a real absence with edges, a mystery made sharper by all the things it is not. Chapter 7. The leading ideas, what dark matter might be made of. Once astronomers became confident that dark matter was not simply hidden ordinary matter, the question changed. The mystery was no longer only about missing mass. It became a question about the inventory of nature itself. If most matter in the universe is not made of atoms, then what is it made of? This is where dark matter research moves from astronomy into particle physics and cosmology. Scientists are not searching for a single poetic answer, but for a physically consistent one, something stable or long-lived, something that contributes gravity, something that does not shine in ordinary light, and something that fits the history of structure formation in the universe. Even now, after decades of work, no candidate has been confirmed. But a few ideas have emerged as the leading possibilities, and each one reflects a different way the universe might be deeper than the standard model of known particles currently allows. One broad idea is that dark matter consists of weakly interacting massive particles, commonly called WIMPs. These are hypothetical particles that would be heavy compared with familiar particles like electrons, and would interact so weakly with normal matter that they could pass through vast amounts of ordinary material almost unnoticed. The appeal of WIMPs comes partly from how naturally they seem to fit both cosmology and particle theory. If such particles were created in the early universe, then, as the universe expanded and cooled, they could have been left behind in roughly the right abundance to account for the dark matter observed today. That possibility made WIMPs especially attractive for many years because they seemed to connect the large-scale structure of the universe with new microscopic physics. NASA still describes WIMPs as one of the major favored classes of dark matter candidates, while also noting that searches have not yet found confirming evidence. Part of the reason WIMPs were taken so seriously is that they gave scientists several different ways to search. If WIMPs occasionally collide with ordinary nuclei, then extremely sensitive underground detectors might notice the tiny recoil from such an interaction. If WIMPs can annihilate with one another, then telescopes looking for gamma rays or other high-energy particles might detect the products of those encounters in space. And if WIMPs are connected to theories that extend the standard model, particle colliders might create related phenomena in high-energy collisions. This made the WIMP idea experimentally powerful as well as theoretically appealing. It was not just a speculation floating beyond reach. It was a target that could be pursued in several different ways. So far, however, the absence of a confirmed detection has made the picture more cautious. WIMPs remain important, but they are no longer treated as the almost automatic answer they once seemed to be. Another major candidate is the axion. Axions were not first invented to explain dark matter. They were proposed in particle physics as a solution to a specific theoretical puzzle known as the strong CP problem. That origin is part of what makes them so interesting. They arise from an effort to make known physics more consistent, yet they may also supply the invisible matter of the cosmos. NASA describes axions as hypothetical subatomic particles that are both low in mass and low in energy, and notes that they have been searched for using data from several space observatories. In contrast to WIMPs, which are usually imagined as relatively heavy particles, axions belong to the opposite intuitive category, extremely light particles that could still make up dark matter because of how many of them might exist and how they would behave collectively. The axion idea is especially elegant because it suggests that dark matter might not need to be heavy in the ordinary sense at all. Instead, it might be made of a vast population of very light particles spread throughout space. These particles would interact so weakly with ordinary matter that they would be extraordinarily hard to detect directly. But under the right conditions, they might convert into photons, or leave subtle signatures in magnetic fields or astrophysical environments. That is why experiments and observations looking for axions often differ from the classic WIMP searches. Rather than waiting for a rare, heavy particle to strike a detector, Some axion experiments try to coax a hidden field into producing an electromagnetic signal. Desai has described axions as an extremely promising dark matter candidate, and major experimental programs continue to search for them. A third important possibility is sterile neutrino dark matter. Ordinary neutrinos are already known particles. They are extremely light, electrically neutral, and famously difficult to detect because they interact so weakly. But the neutrinos in the Standard Model are not suitable to explain all dark matter by themselves. Sterile neutrinos are hypothetical relatives that would interact even more weakly, essentially avoiding the standard weak interaction and revealing themselves mainly through gravity and subtle mixing effects. CERN materials describe sterile neutrinos, or heavy neutral leptons in some contexts, as interesting hypothetical particles that could help solve several major puzzles in particle physics and at the same time provide a dark matter candidate. CERN's lecture notes on sterile neutrinos as dark matter candidates emphasize their possible production in the early universe, their potential radiative decay, and the observational constraints that follow. Sterile neutrinos are especially interesting because they sit at the border between two deep questions. One is the nature of dark matter. The other is the origin of neutrino mass itself. If sterile neutrinos exist, they might help explain why ordinary neutrinos are so light, while also contributing some or all of the dark matter. Unlike many WIMP models, sterile neutrino dark matter is often discussed in the context of warm dark matter rather than strictly cold dark matter, depending on how the particles were produced and what mass range they occupy. That matters because the way dark matter moves in the early universe affects how small-scale structure forms later on. A candidate is not judged only by whether it is invisible and massive enough. It is also judged by whether the resulting universe would resemble the one we observe. There are also candidates that are more exotic still. Some physicists investigate ultralight bosonic dark matter, sometimes described in popular terms as fuzzy dark matter, in which the particle mass would be so small that quantum behavior becomes important on astrophysical scales. Others consider hidden sector particles, dark photons, or more complicated multi-component dark matter models, in which the dark sector has its own internal structure rather than consisting of only one new particle. NASA's dark matter overview notes that scientists think it is possible dark matter could be made up of more than one kind of matter or particle, and that new candidates may continue to emerge. This is an important reminder that the field is not frozen around a few old ideas. The leading candidates are leading only because they have been studied deeply and fit many constraints, not because the universe has promised to choose from a short list. Primordial black holes remain a special case in this discussion. Strictly speaking, they are not new particles at all. They would be black holes formed in the early universe before stars existed, from unusually dense regions collapsing under gravity. NASA still lists primordial black holes among major dark matter candidates and notes that scientists use observational data to search for signatures associated with them. At the same time, many mass ranges in which primordial black holes could make up all dark matter have been strongly constrained by lensing and other observations. So the idea is much more restricted than it once seemed. That makes primordial black holes an interesting candidate, but a more limited one than the broad particle ideas that dominate most dark matter searches. They remain scientifically alive, though no longer as a simple universal solution. What connects all of these ideas is the need to satisfy several very different kinds of evidence at once. A viable dark matter candidate must fit astrophysical observations of galaxies and clusters. It must be consistent with the growth of large-scale structure in the universe. It must not disrupt the successful description of the early universe preserved in the cosmic microwave background. And ideally, it should emerge naturally from a deeper theory, rather than being added in an ad hoc way. This is one reason dark matter research can feel slow. It is not enough to imagine an invisible particle. That particle must make sense across cosmic history, particle phenomenology, and observational limits all at once. This is also why the phrase leading ideas should be heard with humility. WIMPs are still important, but decades of null results have narrowed many once promising regions of parameter space. Axions remain compelling because they solve a separate theoretical problem while also offering a dark matter possibility, but they too remain unconfirmed. Sterile neutrinos are attractive because of their connection to neutrino physics and cosmology, yet they also face tight observational constraints. Primordial black holes can still be discussed in certain windows, but not as a free explanation for everything. Every candidate carries both promise and pressure. The universe has not yet agreed to reveal which, if any, of these ideas is right. In a deeper sense, this chapter is about how science responds when evidence outruns explanation. Astronomers became convinced that dark matter is real in its gravitational effects long before physicists could say what it is made of. So the field now lives in a peculiar and honest state. Strong evidence for existence, weak certainty about identity. That is not a flaw in the process. It is often how understanding actually grows. First, the universe forces a question. Only later, if we are patient and careful enough, does the answer begin to take shape. And perhaps that is where the quiet reflection lies. Most of the matter in the universe may belong to a kind of reality we have never touched directly, only inferred by its influence. We live among stars and atoms, yet the larger structure around us may be built from something stranger and more silent, reminding us that the cosmos can be deeply real long before it becomes familiar. Chapter 8. How scientists are trying to detect the invisible. By the time dark matter became a serious scientific problem, it was no longer enough to infer its existence only from the motions of galaxies or the structure of the universe. Those lines of evidence were powerful, but they left a deeper question unanswered. If dark matter is real, can it be detected more directly? Can scientists do more than observe its gravitational influence from afar? Can they build experiments sensitive enough to catch even a tiny interaction between dark matter and ordinary matter, or at least find some indirect signal of its presence? Chapter 8 is the story of that effort. It is the story of how modern science tries to detect something that appears to pass through the visible universe almost without leaving a trace. One major approach is called direct detection. The idea is simple in principle, even if enormously difficult in practice. If dark matter particles are passing through our galaxy, then they should also be passing through Earth, through buildings, through mountains, and through our own bodies. If one of those particles interacts, however rarely, with ordinary matter inside a carefully designed detector, it might produce a tiny measurable signal. Because such interactions are expected to be extremely rare, these detectors are usually built deep underground, where layers of rock help shield them from cosmic rays and other background events that could mimic the signal. The goal is to create an environment so quiet that even a faint collision might stand out. Among the best known of these experiments is the Lux-Zeppelin experiment, usually called LZ. It sits deep underground at the Sanford Underground Research Facility and uses a large quantity of liquid xenon as its target material. If a passing dark matter particle were to strike a xenon nucleus, the detector could register a tiny flash of light and a small electrical signal. Those signals would then be compared with the expected signatures of background events in order to determine whether anything unusual had occurred. LZ's official updates report that its increasingly large datasets have not yet shown evidence of dark matter interactions, but they have set some of the world's strongest limits on the kinds of weakly interacting massive particles, or WIMPs, that could still exist. In science, a null result can still be important. It does not merely say nothing was found. It says a growing region of theoretical possibility has been ruled out. This kind of direct detection is both powerful and humbling. It is powerful because it turns an abstract cosmological mystery into a laboratory problem. It is humbling because the challenge is extreme. A detector must distinguish a possible dark matter event from natural radioactivity in the surrounding materials, traces of radiation from space, neutrinos, and even the detector's own internal noise. The deeper the experiment goes and the cleaner its environment becomes, the more sensitive it can be. Yet with every new round of improvement, nature may still remain silent. That silence does not prove dark matter is absent. It may mean the particles are lighter, heavier, or less interactive than the experiment was designed to detect. It may mean the correct model lies elsewhere. Detection efforts therefore proceed by narrowing the search rather than expecting instant revelation. Another path is indirect detection. Instead of waiting for dark matter to hit a detector on Earth, scientists look into space for signals that dark matter might produce by annihilating, decaying, or otherwise affecting high-energy astrophysical environments. NASA's Dark Matter Overview notes that scientists use data from missions such as Fermi to search for possible signatures, including the evaporation of primordial black holes and other phenomena connected with dark matter ideas. In the broader indirect search program, astronomers examine gamma rays, X-rays, cosmic rays, and other messengers from regions where dark matter may be concentrated, such as the centers of galaxies or dwarf galaxies orbiting the Milky Way. The logic is that if dark matter particles can transform into known particles under certain conditions, then the sky itself may serve as a detector. This approach is attractive because the universe contains environments far more extreme than any laboratory on Earth. Dense galactic centers, galaxy clusters, and dark matter-rich dwarf galaxies may all provide conditions in which rare dark matter processes become easier to notice. But indirect detection comes with its own difficulty. Space is full of ordinary astrophysical sources that also produce energetic radiation. Pulsars, black holes, shock waves, and supernova remnants can all create signals that are complicated to interpret. So even when astronomers observe an intriguing excess of gamma rays or some other anomaly, that is not the same thing as a confirmed dark matter detection. The burden of proof remains very high. A candidate signal must be shown not merely to exist, but to resist more conventional explanations. Indirect searches, therefore, live in a careful zone between excitement and restraint. A third route runs through particle colliders, especially the Large Hadron Collider at CERN. The reasoning here is different from both underground detectors and astrophysical searches. Instead of waiting for cosmic dark matter to arrive or hoping it reveals itself in space, collider physicists try to create new particles in extremely energetic collisions. If dark matter belongs to a larger family of unknown particles, some of those particles might be produced in collisions between protons. Because dark matter candidates would not be expected to leave ordinary tracks in the detector, physicists often search for missing energy and momentum that suggests something invisible carried energy away. CERN materials describing dark matter searches at colliders emphasize this logic, and also note that collider experiments are particularly useful in probing light-dark matter and interactions that might not show up clearly in traditional direct detection experiments. Collider searches are valuable because they test dark matter ideas from the side of fundamental particle theory. They do not depend on the local density of dark matter in the Milky Way, and they can explore broader hidden sector models, mediator particles, and interaction channels. At the same time, a collider would not necessarily prove that a newly created invisible particle is the same thing making up the cosmic dark matter. It might reveal new physics without fully solving the astronomical problem. So collider evidence, if it came, would still need to be connected back to cosmology and astrophysics. This is one reason dark matter detection is so difficult. Different methods answer different pieces of the puzzle. A convincing solution may require several of them to point in the same direction at once. Axion searches form another major branch of the effort, and they rely on a very different detection strategy. The Axion dark matter experiment, known as ADMX, is one of the leading official efforts in this area. ADMX is a haloscope, meaning it is designed to search for dark matter axions in the halo of our galaxy by trying to convert them into microwave photons inside a strong magnetic field. The experiment uses a large magnet, a resonant cavity, and highly sensitive low-noise electronics to listen for an extremely faint signal that would indicate an axion passing through the apparatus. This is a beautiful example of how dark matter physics can reshape experimental imagination. Rather than waiting for a heavy, invisible particle to strike a nucleus, ADMX tries to transform a hidden field into detectable light. What makes axion searches especially interesting is that they are not just scaled-down versions of WIMP experiments. They reflect a different picture of what dark matter may be. If axions are very light and very abundant, then dark matter may behave more like a field permeating space than like a sparse rain of heavy particles. That means the search tools must also be different. Precision, frequency tuning, quantum sensitivity, and magnetic conversion become central. ADMX describes itself as one of the flagship searches for axion dark matter, and the only one specifically looking for axions in that particular way. Its continued refinement shows that dark matter detection is not one single hunt, but many overlapping hunts shaped by different theoretical possibilities. There is also a broader observational strategy that does not detect dark matter particles individually, but maps their presence more and more precisely through gravity. NASA's Roman Space Telescope Dark Matter Overview explains that Roman's huge surveys will study the distribution of galaxies and galaxy clusters in order to produce some of the most detailed investigations yet of dark matter through its gravitational effects. Recent web-based work has also produced sharper maps of dark matter by tracing how its gravity influences visible matter and background light. These efforts do not catch the particle itself, but they matter greatly because they tell scientists where dark matter is, how clumpy it is, and how it behaves across cosmic time. Better maps can help refine which particle models remain plausible and which do not. In that sense, gravitational mapping is not separate from detection. It is one of the ways the search is guided. What emerges from all of this is not a single instrument pointed at a single target, but a whole scientific ecosystem. Underground detectors listen for rare collisions. Space telescopes watch for annihilation or decay products. Particle colliders search for invisible outcomes in high-energy collisions. Axion experiments try to convert a dark matter field into photons. Space observatories and large surveys map the gravitational imprint of dark matter on the cosmos itself. Each method has strengths, limits, and blind spots. Each rules out some possibilities, while sharpening interest in others. The fact that dark matter has not yet been detected directly does not mean the search has failed. It means the search has matured. Scientists now know far more clearly what kinds of signals have not appeared, what kinds of models remain open, and how precise future searches must become. There is something remarkable in the patience of this work. The object of the search is not visible and may barely interact with ordinary matter at all. Yet scientists continue building quieter detectors, cleaner experiments, deeper surveys, and sharper theories. The hunt for dark matter is therefore not only a hunt for a particle. It is a test of how far careful reasoning and instrument making can reach into the unknown. The invisible is being approached from many sides at once, not by intuition alone, but by disciplined persistence. And perhaps that is where the quiet reflection belongs. The universe may be filled with something we still cannot touch directly, yet we keep learning how to listen for it in silence, in starlight, in collisions, and in the bending of distant light across space. There is a strange comfort in that effort, as though the cosmos does not yield its deepest truths quickly, but it does allow them to be approached, little by little, by minds patient enough to keep searching. Chapter 9. Could we be wrong? Alternatives to dark matter. Science becomes strongest not when it protects a favored idea, but when it keeps asking whether that idea is truly necessary. Dark matter is a powerful explanation for a great range of observations, but it is not the only kind of answer that has been explored. From the beginning, some physicists and astronomers have asked whether the missing mass problem might instead point to something more radical. Perhaps the universe does not contain a large amount of invisible matter at all. Perhaps what needs revision is gravity itself. Perhaps the laws that work so well in the solar system and in the laboratory do not remain exactly the same in the faint, low acceleration environments of galaxies, or on the largest scales of the cosmos. Chapter 9 is about that possibility. It is about the serious alternatives to dark matter, why they were proposed, what they explain well, and why most scientists still conclude that dark matter remains the more successful framework overall. The best-known alternative is called modified Newtonian dynamics, or MOND. Proposed by Mordechai Milgrom in the early 1980s, MOND begins from a simple thought. The mismatch between visible matter and observed motion in galaxies might not require unseen matter if the ordinary laws of motion or gravity change behavior at extremely low accelerations. In MOND, the departure does not happen in strong gravity settings like the inner solar system, where conventional Newtonian and relativistic gravity work extremely well. It is meant to appear in the gentler outskirts of galaxies, where the observed discrepancies become most obvious. In that sense, MOND is not primarily an attempt to explain every cosmic mystery at once. It was first designed to address the regularities of galaxy rotation without invoking an invisible halo of matter around every galaxy. One reason MOND has remained scientifically interesting for so long is that it does achieve real successes. It was not invented as a vague philosophical protest against dark matter. It was invented to make quantitative predictions for galactic dynamics, and in some contexts, those predictions have been remarkably sharp. In particular, MOND naturally captures certain tight relationships between the observed distribution of ordinary matter in galaxies and the measured acceleration of stars and gas. Recent reviews note that MOND performs especially well for galaxies' radial dynamics and for the radial acceleration relation, which links the acceleration inferred from rotation to the amount of visible baryonic matter present. This is part of why the idea has not disappeared. Even scientists who favor dark matter often acknowledge that MOND identified an important empirical regularity that any successful theory of galaxies must somehow explain. That point matters because the debate is not between a sensible theory and a foolish one. It is between two different strategies for explaining the same broad problem. The dark matter strategy says that gravity is basically correct as currently understood, but an unseen matter component supplies the extra pull. The MOND strategy says that the observed gravitational behavior itself changes in a predictable way in very low acceleration regimes, reducing or even removing the need for large quantities of unseen matter in galaxies. Both approaches are responses to real data. Both have motivated decades of work. The question is not whether the alternatives are serious enough to be discussed. They are. The deeper question is whether they can explain the full range of observations as successfully as dark matter does. This is where the picture becomes more difficult for modified gravity ideas. MOND was designed with galaxies in mind, and galaxies remain its strongest arena. But the universe does not only present the missing mass problem in individual galactic rotation curves. It appears in galaxy clusters, in gravitational lensing, in the cosmic microwave background, and in the growth of large-scale cosmic structure. A successful alternative to dark matter must do more than explain galaxies elegantly. It must also account for these broader systems without generating new contradictions. Reviews of MOND's observational record emphasize exactly this tension. The idea can do impressively well in some galactic cases, but it struggles in others, and it has long faced major problems in galaxy clusters, where a residual missing mass problem remains even after the MOND modification is applied. Galaxy clusters are especially important because they are rich, multi-component systems. They contain galaxies, large amounts of hot gas, and strong gravitational fields traced by lensing. In the standard dark matter picture, the cluster problem is an extension of the same logic seen in galaxies. There is more gravitating mass than visible matter alone can provide. In the MOND picture, however, the modification that helps with galaxies does not fully remove the discrepancy in clusters. A recent lensing-based study notes that MOND has long been known to fail in galaxy clusters in the sense that a substantial residual missing mass problem remains. In fact, the authors discuss how this residual component behaves in a way that still looks effectively collisionless, much like the usual dark matter invoked in the standard framework. That is a serious difficulty for the idea that a modified law alone eliminates the need for unseen mass. Colliding clusters sharpen this problem further. In systems like the Bullet cluster, astronomers observe a separation between the ordinary hot gas, which interacts and slows during the collision, and the dominant gravitating mass traced by lensing. In the standard dark matter picture, that separation makes sense if most of the mass belongs to a collisionless component that passes through the collision more easily than the gas does. Modified gravity theories have a harder time reproducing this kind of geometry without reintroducing additional unseen matter-like components or more complicated extra fields. Even some work within MOND-related frameworks acknowledges that colliding clusters indicate a residual unseen mass component behaving much like ordinary dark matter. That does not automatically kill all modified gravity models, but it does weaken the claim that altered gravity alone is sufficient. The cosmological scale is another challenge. The standard dark matter framework is deeply woven into the successful modern description of the early universe, the cosmic microwave background, and the growth of large-scale structure. Alternative gravity theories must therefore do more than repair galaxy dynamics. They must reproduce the acoustic peaks in the microwave background, the timing and amplitude of structure formation, and the observed distribution of matter across cosmic time. This has proven difficult. A recent review in Nuclear Physics B argues that any complete solution to the dark matter problem must handle the fine details of structure formation and cosmology coherently, not only galactic phenomenology. That review also notes that new modified gravity theories are being developed that perform better than earlier attempts, including models built to address Planck observations. But it presents this as an emerging research frontier rather than a settled replacement for dark matter. This is an important nuance. Saying that dark matter remains the dominant explanation does not mean modified gravity is dead. It means the burden of success is very high. A replacement must explain not just one beautiful pattern, but the whole connected web of evidence. Some theorists continue developing relativistic versions of MOND and other modified gravity frameworks exactly because they hope to achieve that broader consistency. The recent literature shows that this work is active, and in some cases quite sophisticated. But the same literature also makes clear that the alternatives are still struggling with major observational demands, especially in clusters and in cosmology. There is no consensus that a fully successful alternative has yet emerged. There is also a middle ground that sometimes appears in modern discussion. Some researchers investigate whether the true answer could involve both a dark matter component and some modification of gravity, or whether baryonic feedback processes inside galaxies might partly mimic patterns that MOND highlighted. This reflects a broader truth about science. When one idea identifies a genuine empirical regularity, the winning theory often needs to absorb that insight rather than dismiss it. Even if dark matter is real, the close relation between visible matter and galactic dynamics that MOND emphasized still demands explanation. Some modern researchers therefore see the debate not as a simple winner-takes-all contest, but as a pressure test that has forced the standard picture to become more precise about how galaxies actually form and evolve. Space missions are helping with this question by measuring cosmic structure more precisely. ESA's Euclid mission is designed to map the geometry of the dark universe by measuring galaxy shapes, weak lensing, and clustering across enormous volumes of space. Those observations are meant to test dark matter, dark energy, and gravity together through their effects on the evolution of cosmic structures. That is exactly the scale on which alternatives can be judged most strongly. A modified gravity theory cannot merely work in isolated galaxies if it fails when confronted with the full statistical structure of the universe. In the coming years, these precision surveys may narrow the space for alternatives even further, or perhaps reveal subtleties that keep the question open. Either way, the matter will be decided less by taste than by measurement. So could we be wrong about dark matter? In the strict scientific sense, yes. Any unconfirmed component of nature remains open to challenge, and serious alternatives deserve investigation. That is part of what keeps science honest. But based on the current balance of evidence, the alternatives have not yet displaced dark matter as the leading framework. Mond and related ideas illuminate important features of galaxy dynamics and remind physicists that the visible distribution of matter is more tightly connected to motion than a naive picture might suggest. Yet they continue to struggle with clusters, lensing, and cosmology in ways that the dark matter framework handles more naturally. The result is not a final verdict written forever. It is a present judgment based on which explanation currently does the best total job. There is something quietly profound in that uncertainty. The universe may be telling us either that most matter is invisible, or that the law we trusted needs to be deeper than we imagined, or perhaps that both ideas touch part of the truth. And maybe that is one of the gentlest lessons in all of cosmology. That reality can remain stable enough to study while still being strange enough to surprise us, and that doubt, held carefully, is not a weakness, but one of the ways we move closer to what is real. Chapter 10. The quiet mystery of a universe built on the unseen. When people first learn about dark matter, the immediate reaction is often one of surprise. It can seem almost unreasonable that so much of the universe could be structured by something that has never been directly seen in the ordinary sense. But by the end of this story, the surprise becomes quieter and deeper. Dark matter is no longer just a missing ingredient in a scientific equation. It becomes a new way of understanding what kind of place the universe is. The visible cosmos, for all its beauty, may be only the illuminated fraction of a larger reality. Galaxies shine, stars burn, gas glows, dust scatters light, and planets reflect sunlight into the dark. Yet the broader architecture around them appears to be shaped by something that does none of those things. Modern astronomy increasingly suggests that the universe is not built only from what reveals itself, but also from what can be known only through influence. That idea has consequences far beyond the technical question of what dark matter is made of. It changes the meaning of cosmic structure itself. A galaxy is not simply a bright system of stars arranged into a disk or an ellipse. A galaxy cluster is not merely a crowded region where many galaxies happen to gather. On the largest scales, the universe resembles a vast network of filaments, nodes, and voids, a cosmic web in which matter is distributed in patterns that grew over immense stretches of time. According to NASA's overview of large-scale structures and recent Hubble mapping work, this web-like structure is largely made of dark matter, which acts as a gravitational scaffold guiding the visible matter we later observe in galaxies and clusters. In that picture, starlight does not define the true skeleton of the cosmos. It traces it. The visible universe is not separate from the unseen one, but nested within it. This is part of what makes dark matter such a quiet mystery rather than a theatrical one. The evidence for it does not come from a single shocking event. It comes from consistency across very different scales and methods. The motions of galaxies suggest more mass than visible matter alone can provide. Gravitational lensing reveals stronger warping than ordinary matter allows. The large-scale arrangement of galaxies fits the growth of structure in a universe whose mass is not mostly atomic. Modern space observatories can now map the influence of dark matter across huge regions of sky, showing that what once existed only as an inference now has a measurable large-scale imprint. A recent NASA image release using web data describes a dark matter map laid over a field containing hundreds of thousands of galaxies, with the invisible substance traced through its gravitational influence on ordinary matter. This is an extraordinary moment in the history of science. Not direct visibility in the everyday sense, but a refined and powerful way of making the unseen measurable. And yet, despite all of this, the central identity of dark matter remains unresolved. Scientists can describe what it appears to do far more confidently than what it is. It seems to outweigh ordinary matter by a large margin. It seems to help organize galaxies and larger structures. It seems not to interact with light in the usual electromagnetic way. But whether it is made of weakly interacting massive particles, axions, sterile neutrinos, some hidden sector field, primordial black holes in restricted ranges, or something else entirely remains unknown. NASA and ESA both describe dark matter as an unknown component that contributes to the gravitational field of the universe and outweighs ordinary matter, while also emphasizing that its true nature has not yet been identified. This combination of confidence and uncertainty gives dark matter its special character in science. It is not a fantasy inserted to fill a gap. It is a measured necessity whose underlying substance still waits beyond the edge of present knowledge. Perhaps the most important lesson in all of this is methodological. Dark matter shows that science does not depend only on seeing things directly. It often depends on reading effects faithfully enough that hidden causes become unavoidable. A planet can be discovered from the wobble of its star before anyone images it. A black hole can be inferred from the motions of nearby matter before its shadow is seen. In a similar way, dark matter entered science because gravity kept pointing beyond the visible. The universe, in effect, weighed more than it shone. That is a deeply scientific kind of mystery, not a mystery of fantasy, but a mystery forced upon us by repeated observation. The hidden component was not invented because invisibility is romantic. It was inferred because the alternative explanations failed to account for the total pattern. The future of this mystery is likely to be shaped by even larger and more precise maps of the dark universe. ESA's Euclid mission is built to investigate the geometry of the dark universe by measuring the shapes and redshifts of galaxies across a vast region of sky, while NASA's Roman Space Telescope is designed to study dark matter through wide-field surveys of galaxies and galaxy clusters. ESA explains that Euclid will trace the hidden web-like foundations of the cosmos and map billions of galaxies, helping scientists study how the universe formed and evolved over cosmic history. These missions matter because dark matter is not only a particle problem, it is also a structure problem. The more accurately scientists can map where dark matter is and how it behaved over time, the more tightly they can test the theories about what it may be. The invisible becomes more constrained, more shaped, less vague. Even without a final particle identification, the dark universe is gradually becoming a more detailed physical landscape. There is also something striking in the fact that ordinary matter, the material of stars, oceans, mountains, bones, atmosphere, and memory, may be a minority form of matter in the cosmos. NASA's dark matter overview states that ordinary matter makes up only a small fraction of the universe, while dark matter contributes a much larger share, and dark energy dominates the total mass energy budget even further. ESA's dark universe materials make the same broad point. Most of the universe is not made of the familiar atomic matter from which everyday life arises. Human experience is therefore built from a special and luminous subset of cosmic reality, not the dominant one. We are made of the kind of matter that glows in stars, forms chemistry, and builds complexity, but we seem to live inside a much larger framework whose dominant ingredients remain mostly hidden from direct view. That does not make ordinary matter unimportant. In fact, it may highlight how unusual it is. The visible universe contains the processes that lead to stars, planets, atmospheres, oceans, biology, and conscious observers. Dark matter seems to provide structure and gravitational depth, but not the chemistry of life as we know it. The relation between the visible and the invisible is therefore not one of rivalry, but of dependence. According to NASA's Building Blocks overview, dark matter forms a gravitational scaffold that attracts most of the cosmos' normal matter. That ordinary matter later becomes the familiar visible universe. In a quiet way, this means that the stars people have looked at for thousands of years may owe their large-scale placement to something no ancient observer could ever have imagined. The luminous cosmos may be the flowering surface of a hidden gravitational foundation, and still, the mystery remains open. Dark matter may turn out to be a new particle. It may belong to a hidden sector with its own rich physics. It may reveal itself through a detection experiment, through a cosmological survey, or through a theory that unites presently separate puzzles. Or the current framework may one day be revised by an even deeper understanding of gravity and matter together. Science has not promised closure on a human schedule. What it has provided is something perhaps more valuable, a steadily sharpened picture of what the universe is asking us to explain. Dark matter is one of those rare ideas that grows more astonishing the more soberly it is studied. The better the measurements become, the harder the question presses. There is a calm kind of wonder in that. A universe built partly on the unseen is not necessarily a colder universe. It may simply be a deeper one, where reality does not end at the edge of light, and where what holds things together can remain hidden while still being true. And perhaps that is a gentle thought to end on, that existence may be shaped in large part by what does not announce itself, and yet the unseen still leaves its imprint everywhere, quietly guiding the galaxies, patiently surrounding the stars, and holding the visible world inside a larger dark embrace. And now, my friend, as this quiet journey through dark matter comes to an end, you can let the mystery stay with the stars while your mind finally rests. If you're still awake, there's another sleepy science video waiting for you on the channel. But if not, just close your eyes, drift a little deeper, sweet dreams among the stars.